Okay, so we spent most of the last hour talking about organizing categorical data and surveys and stuff like that. We want to start off the second hour here with organizing numerical data. Numerical data is just slightly different. Numerical data, you don't have a preset number of categories. At color, we were able to narrow it down to 3 colors, or a yes or no question, or whatever. Numerical data can be divided into 2 pieces. Something called discrete. This is not, your test won't be quite this technical, and continuous. But I have to point them out because the way we organize them is very different. Discrete numbers are basically counting. How many cars do you own? You can count them. 1, 2, 3, 4. How many kids do you have? Count them, 1, 2, 3, 4, whatever. Continuous is measured. How tall are you? How much do you weigh? Now, there are some that are in a gray area. Is money discrete or continuous? Well, you can count money. It's discrete. Age, is that discrete or continuous? Well, you can count your number of years, but it's technically measured. Time is a measurement. So, I mean, and age is some people would classify age as discrete. So, I mean, there's a gray area there, is all I'm saying. But for discrete numerical data, if I want to organize it, it is very, very much like organizing categorical data. Let's say I want to survey households to see how many cars are in a household. And let's say for this survey, nobody answered more than 4. And let's say we're in town, we're surveying people in town or in city. So we want to know people, families, households within the city limits. So we actually have some with no cars. You get outside the city limits, there's very few families without a car. Let's say it breaks down like that. So now I can just do a bar graph that's going to have all those numbers on it. 0, 1, 2, 3, 4. The difference is when I do my bar graph, and I'm not going to actually number up the side here, does 0, 1, 2, 3, 4, do they have to put in that order? Yeah, they should. It should be because we're counting 0, 1, 2, 3, 4, or the other way around, 4, 3, 2, 1, 0. Yeah, but remember when we were talking about red, green, blue, I made a point to point out they could go anywhere. Red, green, blue, blue, green, red, blue, red, green, whatever. You can put them in any order. Numbers, numerical data, has a logical order. And generally you do go smallest to largest. So when we put in the bars, 8 would be something like that. 19, a little bit taller. 28, taller yet. What do you notice about the way I'm drawing these bars? They're tight together. There's no space between them. That is, we talked about that psychology of statistics. This is actually working with the psychology. For the colors, the bars were separated because there is no logical connection between red, blue, and green, other than their colors. There's no logical order. So they separate them to actually honestly portray to your brain that there is a separation between these. Here they put them together to honestly portray to your brain that there is a connection to these. They do go together like that. If you ever see categorical data like colors or whatever with the bars tight together, they're trying to deceive you. They're trying to show a connection that isn't there. Let's talk now about measured data, continuous data. Let's talk about height. Now, for the number of cars owned, we could list out, for most discrete data, we can list out all the possibilities, just like we do with categorical data. With continuous data, we can't. Let's say height. I'm just going to list out a few heights here. Let's say we have people listed at 63.2 inches, 63.8, 64.1, 64.3, 64.6, 64.9, 65.4, 65.7, 66.0, 66.3, 66.4, 66.8, and so on. We keep going up. There is no way we can list every possible value. Not only that, but there's not going to, the bars would all be really short because there's only, the chance of someone having exactly the same height is pretty small when you're going down to the 1/10 of an inch. If you have a really big group, I suppose there's maybe a few that are exactly like 64.3 or whatever. So what we do is we group the data. So we might do from 63 to 63.0 to 64.9. 65.0 to, what's this going to have to be? Well, one of the major things with the groups in order to be done well is that each group must be the same size. So to be the same size, this would have to go to 66.9. Then 67.0 to 68.9, and so on. So now when we do our frequencies, what we're getting is the frequency of a group. So 63.0 to 64.9 is going to be this. Oops, sorry, not there. This group right here, 1, 2, 3, 4, 5, 6. There are 6 people that were within that range. And that's what this is, still might be labeled as height, but it might be labeled as height classes or height ranges or something like that. This is still going to be labeled as frequency. And again, this would be put in a bar graph, or what we call a histogram, where this is 63.0 to 64.9, make the bar up to 6. 65.0 to 66.9, make the bar, and again, they're tight together like that. Now, I'm not going to get real choosy about this, but just so you know, when you hear the word bar graph and the word histogram, that is the difference. A bar graph is showing categorical data, and a bar graph should have spaces between the bars. A histogram is showing numerical data, and the bars should be tight together because there is that connection between each group. And we're not going to go off on that for any longer. There is another type of graph that doesn't necessarily have to do with organizing a large set of data. What it has to do is following a single data point over time. Let's say I'm going to do a graph of your cost of tuition per credit. And yes, I am going to cheat. I'm going to break my graph here. It's like 147 or something like that now, isn't it, per credit? When I started here in 2000, it was 98 bucks a credit. 2005, it had gone up to about 111 bucks a credit. Between 2005 and 2010 is when it took our big jump up to, it was like $141 a credit. Now in 2015, it's right around that, 150. Now, one thing a lot of people want to do is this. See that little blue line I just put in there? That blue line's meaningless. In fact, it's actually deceiving because we didn't start out at 0. So that don't fall into that trap. This is what we call a line graph. And a line graph shows change over time. What's along the bottom is always dates, whether it's years, months, day of the week. You might show sales from Monday, Tuesday, Wednesday, Thursday, Friday, or whatever. The advantage of a line graph, again, just like a bar graph, it's really tough to get exact numbers. If I asked you what was the tuition in 2015, well, I don't know, was it 108, 109? What was it? It's hard to get an exact number. But what a line graph is very, very good at is saying, when is it increasing or decreasing? Obviously, the line here is going up, so it's increasing. In fact, on this line graph, it's always increasing. There hasn't been a drop in tuition since I started here. If it was going down, of course, that would mean it would be decreasing at that point. Also, if I were to ask you between what two measurements was it increasing the fastest, what are we going to look for? How steep it is. The steeper the line, the faster it's increasing or decreasing. It's really steepest there, so it's increasing the fastest between 2005 and 2010. Now, that doesn't mean that that all happened at once. I mean, obviously there's, it changed every year. The points may have looked, weird in between there, but we chose those two benchmarks, those two snapshots to take at those times. Okay. Well, that is enough about organizing data. I want to take now a look at doing some calculations with data. We're going to talk, when we talk about, what we've been doing is summarizing data pictorially with graphs and tables, whatever. We want to look at summarizing data numerically. To understand that, we must understand what a distribution is. So to do a distribution, what I'm going to do is I'm going to start out with just a number line to illustrate this. And let's say we want to look at grades on tests. Let's say the lowest test score we have is 60. I didn't make that work out real well, but we'll stop at 100 there. So pretend this over here doesn't exist. And let's just, every time someone gets that grade, we're going to put a dot there. So someone scored a 77. We're going to put a dot. Actually, I don't want to put it right there. I want to put it, I want to put it up above slightly. So 77, I'm going to put a dot right above the 7. Somebody scored an 82, put a dot there. 91, put a dot. Another 77, I'm going to put a dot slightly above it. 79, put a dot there. 84, another 77, put another dot there. Another 91. And what happens here is these dots fill in. The numbers that occur the most, what happens to them? It gets taller there, right? And what we do is we can draw in kind of a smooth curve for these dots like that. Well, this one looks really weird because it was a small number. But if we had a large, let's say we compiled the scores on this same test year after year after year, that curve might start to look something like this. In fact, it will start to look something like that. What does the height of that curve indicate? Well, here, that's the number of people that scored an 89 on that test. Well, what score happened more often, the 89 or an 85? How do I know 85 occurred more often? Because the curve is higher there, it's taller there, right? So more people had an 85 than 89. In nature, natural things like test scores tend to, in nature, height of people tends to do this way. Most things follow a curve similar to this, and it's called a bell curve. You've probably heard the term bell curve before, or grading on a curve. The technical name for a bell curve is called a normal curve. Now the term bell curve was put in there to kind of make it, because it's shaped like a bell, to kind of give people a visual. Normal curve is the official name, the formal name of it, and it was called that because in nature, values normally occur like that. Distributions normally look like that. So if I'm looking at that distribution, let's say I have a test here. And I'm looking at distribution of scores. There's two things about that curve that I can describe. First of all, the center of that curve is right here. But what else could change? Could I draw a curve that had that same center, that was drastically different from this curve, and still be a bell curve? Sure I can. Those two curves, the purple and blue curves, have the same center? Are they alike? Not really. The purple one's way narrower, right? The blue one's way wider. What this is saying is, the blue one's saying, yeah, the center is at 81 or 82, but the scores are really spread out. Some people scored really low, some people scored really high. But the purple curve is saying, yeah, the center, the highest, the most common score was 81 or 82. And almost everybody was really close to that. That is what we call spread. So now I could take that purple curve, the width of the curve is called the spread. I could take that purple curve and put it over here and change its color. Now the purple and the green curves have the same spread, but they have a different center. Center is moved. The spread is the same, but the center is moved. This one's got a little spread, the blue one had a big spread. Green and purple have small spreads. So if we can describe the center of the curve, the location of the center, and the spread, how wide the curve is, we can adequately summarize a set of data. Now, some data is what we call skewed, and we're not going to get into that. That means it's not quite a perfect bell. It's got one side is stretched out a little bit. But for our purposes here, because we only have a couple nights to talk about statistics, we're going to talk about perfectly or relatively close to normal curves. So not going to deal with skews. So let's look at measures of center. Well, we have three common measures of center and another one that I'm going to throw in there because it gets used. We have mean, median, mode, and the one I'm going to put in there is also the mid-range. To calculate the mean, add them up and divide by n. Now I'm going to tell you what n means. N is the number of items in a list. So if I have 5 numbers, if I'm going to find the mean, I add them up and I divide by 5. If I have 3 numbers, I'm going to find the mean, I add them up and divide by 3. Perfect. The median is just the middle number. So for the median, we put them in order. Smallest to largest, or largest to smallest, whichever. Usually smallest to largest is the way to do it in statistics. And you find the number that's in the middle. The mode is the number that occurs most often. The mid-range requires us to define two other terms. The min, or the minimum, is the full word. What do you think the minimum is? The smallest number. Smallest. Plus the max, or the maximum, which is the highest number. We add them together and divide by 2. That's the mid-range. So we're going to look at 2 sets of data. We'll do some calculating with them. First of all, if you look at my 2 sets of data, what looks peculiar about them?
There's 12, so that's your number.
Well, I mean, just look at the numbers themselves. Not worried about middles or anything like that. Centers.
The same except that
Yeah, same set of data, but this one has a 72 on the end here. That's significant. Let's find the mean for this set of data. How do I find the mean? First of all, what's n equal for that set of data? 1, 2, 3, 4, 5, 6, 7. N equals 7. So to find the mean, I'm going to add them up. 7 plus 11 plus 12 plus 12 plus 14 plus 18 plus 26. Which is, does it come out to be 100? Wow, that's good. So 100 divided by 7 is what? 14.2857143. Yeah. 2857143. We'll go 14.28. Oh, 29 actually, if I'm going to round, because 285. 14.29. That's our mean. That's pretty simple. We just add them up. Now, one thing I'll tell you on your calculator, before you hit divide, you add them all up, then you hit equals before you hit divide by 7. Otherwise, it does really weird things. To find the median, I first must find the location. The location is found by taking 0.5. 0.5 or 1/2 times n. So 0.5 times 7, because n is 7. You guys remember what n is? The number of items in the list. 0.5 times 7 is 3.5. If we get a decimal, we always round up. Half. Median is middle, it's halfway.
Oh, half of the 14.
Yeah, well, 0.5 is just half, period. 0.5. 7 is the n. That's the number of items in the list. So we're finding median, it's always 0.5 or 1/2 that we use. So we got 0.5 times n, or 0.5 times 7 is 3.5. Since that's a decimal, we round it up to 4. What that is saying is the 4th number in the list is our median. Now, remember, the list has to be put in order from smallest to largest. I already did that when I made the list. So we're just going 1, 2, 3, 4, 5, 6, 7. The 4th number in the list is 12. So the median is 12. Some of you already calculated the mode. What's the mode? 12. That's pretty easy. It's the most often. The only number that appears more than once is 12. Mid-range. Oh, off your notes, what's the smallest number? Largest number? 26. Add that together. It's 33 divided by 2 is 16.5. Notice the mid-range isn't even close to the others, really. Now, if I were looking at these Which one of these do you think is the best measure of center? We're going to rule out the mid-range. That's one that's just used for certain special applications, but I wanted to show you how to do it. But we have the mean, the median, and the mode. Which one do you think is the best measure of center? Most people would usually answer the mean, actually, because the mean, it just feels satisfying. You add them up. Now, I'm not saying it is the best. I'd say most people actually answer that when I ask that question, is the mean. You're actually right, Angie. The median is considered to be the better measure. And the reason why is the reason why I made this second set of numbers the way I did. We're going to come back to the mean here, but let's find the median. What's n for this set of numbers? 8, right? There's now 8 of them. So what's the location going to be? Well, it's 0.5, again, that 1/2, times what? 8 gives me 4. Now over here, this was a decimal, so we rounded up. When it comes out to be a whole number, like this one does, it is between that one and the next one. So we got a 4 there. That means that the median is between the 4th and 5th. So the median here is between the 12 and the 14. How do we find what's in between them? Add them together and divide by 2. 12 plus 14 divided by 2 is 13. What's the mode of this set of data? Still 12. We can all agree that the mode is not a very good set of data, measure of center. There's only specialized applications where the mode is used. If you're marketing and you know that you're going to have a very, very narrow focus on your marketing, you want to focus on the mode because that's the one that has this the most often. That's going to give you the most sales for a small amount of, more bang for your buck, I guess. Let's go back to the mean. If we add those all up, get 172. Divided by 8 is going to give us 21.5, correct? Okay, now let's look at this. Over here, we had a median of 12. I added this one really large number of 72. The median jumped up to 13. Not a big change, right? Over here, we had a mean of 14.29. We added that one large number. It jumped up to 21.5. Guess what? Now there's only 2 numbers bigger than the mean. It's not really in the center. The mean is not stable. The median is more stable than the mean. That's why most statisticians claim that the median is the best measure of center. Let me give you an example that proves that point. I believe it was 1982. Either 1982 or 1983. I don't remember exactly. University of Virginia. Advertised. A graduate from their 4-year marketing program that year. Average starting salary. Just under $78,000 per year. Let's put this in perspective. First of all, right now, if you offered me a job about paying $78,000 per year, you might not see me in here again. I'm guessing if I offered any of you a job for $78,000 a year, you might have the same response. In 1982, the average high school teacher was starting out at about $16,000 or $17,000 a year. So $78,000 starting salary is a huge starting salary. Is it an honest statistic? Did they screw something up? No, that's an honest statistic. So how is it possible that the average graduate from their 4-year marketing program was making $78,000 a year? the mean. That was the actual mean. What they neglected to tell you in that statistic there was one of the graduates that year with a degree in marketing, he did finish his degree and graduate, was the man by the name of Ralph Sampson. Mr. Sampson was 7'2". Actually, 7'2" or 7'4", I don't remember now. Two-time, both junior and senior year of college, NCAA Basketball Player of the Year. Guess what he did after college? Played for the Houston Rockets. He was in the NBA. Drafted #1 overall. Guess how much he got paid that year? No. A couple $1,000,000 or more. But he still graduated from marketing. Guess how many $20,000 a year marketing graduates it takes to take the mean of a couple $1,000,000 basketball contract, probably a $10 million basketball contract, down to $78,000. A lot. Mr. Sampson was the only one in the group that made more than $37,000 that year. The only one out of several hundred graduates. In fact, the median was just over 21,000. That's why that whole point of the median being more stable. Here, one real, and this is extreme when you have numbers that vary between 19 and 37,000. Then you got one up there that's like 5 or 6 million. I mean, that's an extreme difference. But that one extreme number can really change a mean. But it doesn't change the median so much. Because the median is always in the middle. Half of the numbers are smaller than it, half the numbers are larger than it. It just isn't as satisfying because that mean, you get to add numbers up and divide. You're cranking out a formula and it feels really good. I know, it's weird. But you guys get the point. So with that, we'll leave you at that. Those are our measures of center. Next class, we will talk about measures of spread and how we calculate those and what we'd use some of this stuff for. And if there's time, we'll do a little bit of review for our Unit 4 test coming up next week, Thursday. For now, you need to worry about a new quiz, which is due tomorrow. That would be Friday at 11:59 p.m. And new homework, which is due for next Tuesday. The computer lab next door is open if you want to work on your quiz or homework.